There we go. We are recording now. We got people online. And first thing first. All right. Um, Vibe coding. How many people have tried vibe coding? Nobody has. Okay, so what do you think? It's bad. All right. So I'm gonna introduce vibe coding just so that people know that I did not make up this term. It's basically it's this term was coined in February this year. So it's only about 3 months old. So it refers to people using natural language to describe to an LLM what a program is supposed to do, and then have the AI, the LLM, to come up with the actual code with in whatever programming language that application is supposed to be programmed in. Um, I have not tried it, so I cannot give you any first-hand experience description about it. But at its best, okay, it is kind of like, if you think about coding, like manual, typical, coding as walking, hiking, okay, this is kind of like giving you a taxi ride, okay, at its best, okay. The question is, can you speak the language of the taxi driver? In other words, like for me, if I were to go to a small town in Spain or Italy, because I don't speak Spanish nor Italian, so I can get into a taxi, it won't help me a single bit because I cannot tell the driver where to go. Now, on the other hand, if I am in Hong Kong, okay, I speak Cantonese and I know Hong Kong fairly well, so I can even tell the driver, oh, you can go this route and it'll be a shorter route, okay? Then I'll be good, okay? Instead of hiking or walking for miles, I go like, oh, this is good. Air conditioning, I don't have to walk, it's all good. This is at its best, okay? I don't really know what is the current state since you have you tried that, Scott? Okay. What do you think? Mm-hmm. Okay. All right. Uh-huh. So the question is, can you give it some really old program that somebody else has wrote, and then you tell the LLM, okay, that's not no no specifics. Hands vibe. Okay. Well, okay. Uh-huh. I see. Okay. Okay, so this is why I cannot do vibe coding because I have zero vibe. Just period. Okay, it has nothing to do with what I'm doing or who I'm with or any time of the day or what time of the year. I just have no vibe. Zero. Dead. Nada. So I cannot do vibe coding. I don't meet the prerequisite. Okay. All right. Okay, cool. Yep. Mhm. Mhm. I see. So it's probably okay for some casual coding for people who are just kind of experimenting with stuff and just want to kind of check it out, but not so much for people who want to major in computer science. That's what I'm getting. Okay. All right. Okay. Okay. So I'm gonna ask this question. Uh, The answer is we actually do not know. We know, and we also do not know how LLM's large language model work. This is not just from people who are new to this whole thing and have no really intrinsic understanding of the whole thing. The CEO of who makes Claude, Anthropic. The CEO of Anthropic actually says it himself that We really do not know how LLM works. We get it to work, but we don't know exactly how. So we know at the very lowest mechanism, the lowest level mechanism, like the neural net, we kind of know how that works. But as an overall thing, it is still a black box. People really don't know how it works. So, hmm, I don't think so. But we still do not know how it can grasp patterns. When it has so many different hidden layers. So, it's just kind of interesting, even though we don't know how the black box works, we're now asking the black box to make other white boxes. White boxes referring to actual coding and with algorithms and stuff like that. So I'm not sure where we are heading with all this. Yeah, that's probably, but that's training the neural net itself. But once you have the LLM, you can point it to anything that you wanted to read, and then kind of quote unquote transform the presentation to how you want it to be, and it can do some quote unquote reasoning with that too. All right, so that's the non discrete math topic that I want to kind of talk about a little bit today, because I think you guys really should know about these things. Um, because otherwise, you might get these as interview questions. I'm not kidding you. This part is real. Okay, because you're hmm? Okay. Well, then you have one fewer competition. I cannot compete with you if that is what they want. Uh-huh. And I think the worst thing is, what if the code actually works even the first time? Because if it does work the first time, then nobody's going to look at it until it is until you need to change it, right? So by the time you need to change it, the human who originally prompted the whole system, prompted the whole thing, is probably not around anymore, and then nobody can read that code anymore. Or you need to hire me to read that code, because at that point nobody else can read that code. So, huh? But that means it knows what the code is supposed to do. Aha. Well, that's describing and they're describing because is it actually understanding how the program is supposed to do, what it is supposed to do, and how it works, or is it really just documented at a mechanical level, which is not difficult? I know it can. Um, this is years ago when it first came out. I was already testing the capability of ChatGPT. I found that there are no homework assignments from CISP 360, 400, or 430 that it cannot do. Yeah, yep. Now, how you guys want to interpret that finding is up to you. So he has more challenging homework assignments? Uh, well, that may actually be possible in the near future. All you have to do is to upload your voice, train the network so that they can speak with your voice, and then you just instruct the LLM plus the audio generator. This is what you want to do. I think it's possible. Well, it's a lot more fun that way. Yep. You can even tell the LLM, just put in a lot of that sort of thing, just so that it sounds natural because most people do have a little bit of that. Yep. All right, so we are back to big omega as a function. And what we'll do today, I hope you guys got a chance to practice as I suggested. Because if you did not, then today's lecture may be a little bit difficult to follow. So we'll go ahead and oh, I need to configure my tablet because I want to explain things today using my tablet a little bit at least. Okay, where's my Wi-Fi? There we go. Okay, it picked up the right Wi-Fi station already. Okay, very good. So now to do the screen share, we just need to do this. Super note. There we go. Excellent. All right. So what we'll do is we are going to work out an example, but after I talk about the where's my other window? There we go. All right. So we're going to work out maybe omega 2 of a set that has mm, four items to begin with. Okay, so that will serve as an example of how to understand something like this and how to get it to work. So with that said, I am going to switch to my tablet, probably kind of switch between the two because I have to refer back to the definitions just so that this way we know why I'm doing what I'm doing. But for the time being, I'm going to write down what I want to solve and I'll switch to the tablet screen as soon as I'm done with this. So we'll have A, B, C, and D in a set. And oops. All right. So this is what I want to do. It is to find the omega 2 of a set A, B, C, D, and we're going to work this out. So the first question is what is that? What is the answer? Okay, what does the answer mean in this case? Well, the answer means I am trying to figure out all permutations of choosing two items out of A, B, C, D. You can kind of think of A, B, C, D as marbles, like four unique marbles in a bag. And I want to pick two marbles out of the bag and put it into a test tube. And I want to find out all the different ways of doing that. Okay. We already know the answer. The number of permutation is 4 divided by 4 factorial divided by 2 factorial. 4 factorial is 24 because it's 4 times 3 times 2 times 1. 2 factorial is 2 times 1, which is 2. So we already know that there should be 12 unique answers. The question is, what are the unique answers? I'm not interested in the number of unique answers. I want to know all of the actual answers. All right. So we'll go back to the definition again because I need to follow my own instruction here. So the first thing you want to test is, are we at the base case? Because if we're at the base case, I got the answer already, okay? In other words, no matter what the set T is, it can be empty, it can have a bazillion items in it. As long as I choose nothing out of that set, I know the answer is a set of an empty tuple. Okay, you can have an empty tuple. Essentially, it is an array or a vector that has nothing in it. Are we doing okay so far? All right. So that's a base case. So now we switch back to my tablet here. It does not look like we can apply the base case because omega, this is omega of 2. So, okay, we got some work to do. So now we switch back and go like, okay, but work do we have to do? So I'm going to put an equal symbol here just so that we can expand that in just a little bit. So if we, okay, I skipped over that one. Okay, so when we look at this, we go like, okay, it's not the base case, so we have to apply the general case, which is whatever this I is, we're going to use that I over here. Whatever this T is, we're going to use this T over here. And then we talked about this notation in the previous lecture, and I presented the JavaScript code, I think, in that in that lecture. So I hope you guys remember what the big U notation means. So I'm going to make that assumption, and now we can continue this and go like, okay, so what we need to do, okay, so I have to keep switching around because I need to show you what we are doing. What we are doing is whatever E I choose out of T, this is what we need to do. We make a set out of E, and then we use a Cartesian product with omega of I minus 1, and then the parameter to omega I minus 1 is going to be t, the original set that we started off with, but we take out the element that we put onto the left-hand side of the Cartesian product. Okay, so can someone tell me how many cases do we have? In other words, how many elements do we have in the example that we're looking at? Mm, so how many things are we unioning using the big union? For every element in the parameter of omega 2, we have to do blah, 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 blah. And then we make a big union out of it. So how many things are we unioning? Four. There are four things. Okay. So what you need to do, okay, I'll let you guys choose. What element do you want to start with? Please make it something other than A. B. Okay. So we'll start with B. So we'll look at B and then say, okay, make a Cartesian product with big U of E in what would be this set here? Okay, let's go back to the notations here. Oh, okay, I take it back. It is big omega, not big U. All right, okay. So we take out the big omega. I skipped one step, so we take this out. I do apologize for that. So we want to use big omega. And what do I put here? What do I put here as a subscript? Omega 1, very good. Okay, omega 1 of what is going to be in this set? Yes, ACD. Okay, very good. ACD, close brace, close paren. So this is one of the things we are going to make a gigantic union out of. Is that okay? All right. It's just because I just randomly choose one element out of the original set that turns out to be B. So the next one, I'm going to choose D. Okay, because remember, in a set, there's no such thing as an ordering of items within the set. So this time it's going to be omega 1 of what would be in this set? Because I choose D to be E. Okay, so let's go back to the original notation. So if I choose element D as E, then what I'll be doing here is T, which is A, B, C, D as a set minus the set that only has D in it. So A, B, and C are the only thing left after the subtraction or difference. So now we only have A, B, C in this one. And then we choose A, for instance. Okay, so this is going to be omega 1. I think you guys are getting the pattern here. This is just B, C, D. And then finally, we have B. And this one is omega 1 of A, C, D as a set. And then all of these are going to be unioned. Okay, if I want to use extra parentheses, that's what it is going to look like. Yes. Uh, right, because we got B already. Thank you. So let's fix that because we already have B earlier. So we're gonna switch B and C around. So this is C, this is going to be B over here, and extra parentheses again. There we go. So is this step okay? Does everybody understand why I can expand omega 2 of ABCD as this rather clumsy and cumbersome representation? Okay, good. So what do we need to do now? Well, we look at each omega 1 and then we apply the same thing. Okay, so I'll do it once, okay, because I think once I show one, you guys will go like, oh, okay, we get it. So hopefully that is going to be the case. So now we go look at omega 1 of A, C, D, and then we go like, oh, can we apply the base case? Because the base case is cool because we don't have to do a single thing. We look up the definition and go like, no, because the base case only applies when the number of trial is 0. Okay, we got a 1 this time. So we have to reapply this, but this time I is 1 and T is A, C, D in a set. Okay, so now we go to here and then go like, okay, and we have to re-expand this. So this time, I can choose A first. I can choose C, or I can choose D. If I chose A as E, then I'll be making a Cartesian product with omega 0 because it is 1 minus 1 is 0. But that set, even though it is irrelevant, it has got CD in it. This is going to be uh, AD because C is removed from the set. And this is going to be AC as a set. And all of these, okay, make sure I have the close parentheses. All of these are going to be unioned. Are we still doing okay? All right. So we look at this and go like, okay, so we have to do this all over again. Oh man, omega 0 of CD. Then we look up the definition. So this is why you probably want to put all the definitions in the notes into your own notes on one page, so it's easy to locate it, okay? Because you already know the final exam is open book and open notes. So you can save yourself some time, now by saying, I'm not going to keep track of my own notes. I'll just print whatever tag has and bring that with me. Will it contain all the information that you need? Yes. But can you find it during the final exam? Probably yes. Can you do it in a very quick way? Probably no, because you did not write it. Okay. So that means, you probably want to do something that will make the lookup process, if you need it, to be faster, which means, you are going to have to organize, all the definitions in the way that you think makes sense. Okay. What makes sense to me may not make sense to you. I think that part is really apparent at this point, especially for those of you who are taking my class the second time because you took 310 already from me. So that means, you have to present things and write your notes in the way that makes sense to you. All right. So now we look at this and go like, okay, let's go find the definition. Omega 0 of anything is, oh, we are all done here. Cool. So we could just make a conclusion that this is a set of an empty tuple, but it is not an empty set. Okay, so you can probably imagine that omega 0 of AD looks like this. Omega 0 of AC also looks like this. Are we good so far? All right. So at this point, okay, you might want to jot down the time, which is actually being recorded right now. But if you're looking for that time mark in the recording, it's not going to help you. So you might want to actually write it down, or type it down in your notes because you might want to come back to this point because I'm going to erase stuff and replace them with something else. Okay? Because otherwise I'm gonna have to do a lot more writing, which I'm not gonna do. All right. So if you have so do you guys need more time before I start to change the screen? You guys are all kind of writing down the time mark. Okay. All right. Cool. So now we're gonna do it in a interesting way. So we now take out this, okay? So we are taking out this. We're taking out this because we know the answers to those recursive call already. So we are just substituting the recursive call with the value that the recursive call is going to return. So now we go like, oh, okay, we know the answer to all of those because this one is really just going to be the set of an empty tuple, and once again, the empty tuple. Is that okay? In other words, we are done with the recursive call. We are now backing up from the deepest level of the recursive call. So now we can go like, oh, okay, I don't see any recursive calls here, so I can evaluate the Cartesian product. So what do you think the Cartesian product should look like for the first one? In other words, if I were to separate this out to be a Cartesian product with an empty tuple, but A is not by itself. A is by itself, okay, which is okay. So what would that look like? Technically, what does it look like? And then we will talk about what we can do with that. So what do you get when you have a Cartesian product of two sets? What do you do for the elements on the left-hand side, and what do you do with the elements on the right-hand side to come up with the actual result of the Cartesian product? uh, Concatenation, right? Concatenation. So in this case, technically speaking, you end up with A with a comma and then an empty tuple like that. Okay, so that is technically what the actual result would look like. But we look at this and we can collapse, all the levels of tuples. So we are only left in this case with um, A in a tuple by itself. So the collapsing of the levels of tuples is depends on the scenario. Sometimes we want to do this, and sometimes we don't want to do this. But in this case, we do want to do that. Okay, so we are collapsing all the empty tuples into nothing. So we are removing the hierarchy of tuples. Is that okay? Are we good? All right. So now, once again, you might want to look at the clock and kind of record the time, and then just kind of comment on what we have done so far, because now I can take this away and go like, okay, we know what that becomes, because it just becomes whatever we talked about a little bit earlier. It becomes the tuple with just A in it, and then we can do the same thing with the other two. Okay, so this time we're erasing both at the same time and replacing them both with this is with a tuple with just C in it. This is a set with just D in a tuple, like that. Do we have any questions at this point? I'm basically reapplying the Cartesian product method to the other two pairs of parentheses, and it should be fairly obvious that this is the result. Is that okay? All right. So now we can go like, okay, what is left for us to do? Oh, the union, right? Because we still have this union and this union to perform. So the union, if you remember from our previous class, the union of two sets would be the elements that can be found on at least one of the two sets, right? So now we have three sets, they're all union together, but none of the element overlaps, okay? So we can go like, oh, okay. So now we can take this out, okay? It's ACD, okay? And then we now replace the whole thing with A in its own tuple, C is in its own tuple, and then D in its own tuple. Are we good so far? Yes? Okay? Yep. That's done up here. Mm-hmm. It is, it's this one or this one? I just did what explained how we got to here. Which part of it do you want to re-explore? Huh? Why? Because I said so over here. Because this is how omega of I is defined. Did you write down when I said write down the time? So you might want to ask someone who wrote it down because you might need to rewatch that portion. Unless you have a specific question about which portion of that timeline you have a question about, then I can answer that specific question. But I cannot go back and re-explain the whole thing. Okay, because it is a union of A in the tuple in the set and C in the tuple in the set and D in the tuple in the set. It's the union of those three, and that's why by the definition of union, this is the result of the union. All right. All right, so if this is the result of omega 1 of ACD, do you want me to go through this entire thing for the union for omega 1 of ABC, the omega 1 of BCD, and omega 1 of ABD? Okay, that was quick. That did not require a whole lot of contemplating. It's like, well, should I ask tech to do this or not? No, that was that was quick. Thank you. So that means I can now go back and replace these parentheses with, what looks like this. Okay, basically a pattern. So now we can go back. Okay. So I'll do it one step at a time. Okay. Once again, I think it might be important to kind of jot down in your own notes, what I am doing at a certain timestamp, because this allows you to have your own index back to, explanation of concepts. So now this is being a Cartesian product with A in a tuple, C in a tuple, D in a tuple, and everything in a set. Is that okay? Does everybody understand what I just substituted? Okay, I looked for omega 1 of the set ACD and just replace it with the result that we came up with a little bit earlier. So now the next task is to look at, so we can replace the same thing for the other three omega 1s. So now we go to these omega 1s. Okay, and replace all of those with the matching sets. So there we go, like, okay, so this is the set of A in the tuple, B in the tuple, C in the tuple. This is going to be the set with B in the tuple, C in the tuple, and D in the tuple. And this one is going to be the set of A in the tuple, B in the tuple, skip C, and then D in a tuple, like that. So I'll be doing okay. Okay, so this is kind of the pattern, okay? And now we look at this and go like, oh, okay, so we are really just looking at the Cartesian product on each line. So now we try to solve for the Cartesian products. So now we look at the first one, and then we go like, can we work that out? Okay, so we take that out. We'll put it, I'll just, oh, well, I'll just put it down here. Okay, so we look at the set B, Cartesian product with A in the tuple, C in a tuple, and D in the tuple. So what is the result of this Cartesian product? You can do also the parentheses collapsing. So after the parentheses collapsing, what do we get out of this Cartesian product? Yes, we'll get BA in the tuple, BC in a tuple, and also BD in a tuple, and everything in a set. So I'm just going to pause here for a little bit just to make sure everybody is getting this. Because this is going back to really just Cartesian product, except we got the extra step of collapsing the parentheses into only one single layer. So we good? Okay. So now we can take this and then go back and substitute this portion here. Okay, so I can substitute this entire portion with what we just figured out, which is the set of BA in a tuple, BC in a tuple, and finally BD in a tuple. All right, so I can do the same thing with the other three lines. So now we can now look at this one. It is DABC. Okay, so I'll just do one at a time. DABC. So now this one becomes DA, DB, and then DC. And then now we work with the next one, which is this one here. Okay. And this one is, oh, what is the third one? Oh, starting with A. Okay, so this is AB, AC, AD as tuples in a set. And finally, we get to the last one, which is starting with C. So now we go like, okay, this is CA, CB, and also CD. Cool. All right. Do any one of these four sets to be union? Does anyone, does any, it's the same element appearing more than once in these four different sets. I'm talking about these sets over here. This is set number one, set number two, set number three, set number four. Do they share any elements? It should be fairly obvious that they do not, right? Because everything on the first row starts with a B, everything on the second row starts with a D, everything on the third row starts with an A, everything on the last row starts with a C. And because these are tuples, if the first element are different, then they are different elements. In other words, we cannot possibly have overlaps between the sets, these four sets here, because ordering matters, because they're tuples, not sets. So that means the union is going to be pretty easy to figure out. So once again, you might want to jot down the time, okay? Because this is the last stage. So the laziest way to do this is simply to remove this, put in a comma, and then we remove this, put in a comma. Yes, I'm pretty good at figuring out how to do things. Oh, we also have to take out the open braces, the extra open braces. Take out this, take this out, and take this out. And then voila, we got the answer. Is that okay? All right. So that's how the recursive definition works. So even though I'll be done with this part here, can I switch back to the slide, the other slide? Yep, go ahead. Mm-hmm. Uh-huh. Yes. So this pair of parentheses is syntactically indicating the parameter. Even though two is really kind of a parameter two, but that's just the notation that I chose to use. So this pair of parentheses is no more than just emphasizing that this is the set from which we are getting two items out of. Mhm. But the parentheses here do not have any specific meaning. So it's more like just syntactic. It's not exactly a tuple. All right. So are we good so far? All right. So that's kind of how it works. Okay, you go back to the definition. We just follow these instructions. These are just the symbolic instructions here, and then we figure out how to generate the all the possible permutation outcomes when we have four items A, B, C, D, of which we want to choose two of those items, in permutations, which means ordering is important. Okay. All right. So given this is how omega I of something is defined, do you think it will take how long will it take you to turn this into an actual implementation in whatever programming language you want to use? Should not be taking that long, right? Because as long as union, all the set operations are well supported by whatever programming language or environment you want to use, then it should be fairly easy. Yep. Yeah, that's what I did. I have a pretty extensive library of, set operations because even though the new JavaScript standard or ECMAScript standard includes union intersection in the set as set primitives, when I was using it, it was not supported. And even at this point, it can only, when you have complex stuff like a set versus another set, it only checks the reference, which is quote unquote kind of like the address. So when you have two objects that really are the same, but they're not created at the same time, it was still not considered them to be the same, which is not the proper behavior. So I still need my own code to implement union intersections and so on. Yep. All right. So given the time that we have or lack thereof, I am going to skip over, the combination outcome set because it's kind of the same thing, except, instead of tuples, we have sets. Okay, the notation is even harder to understand because we have, kind of like a nested big U notation, and this big U notation makes use of the recursive call to get the elements that you can get they it can use. So it is a little bit harder to understand, from that perspective. But it's about the same thing, except this one returns the number of combinations, or it returns the actual combinations when we choose I item out of a set X. So the definition will give you the actual combinations. All right. Significance. Okay, so why is this important? Counting is important because it is the denominator of discrete probability. So that means when we want to figure out what are the chances of, okay, it's usually expressed as a ratio. It is expressed as a ratio of something over the cardinality of the outcome set. So out of all the possible outcomes, the outcomes that you are interested in, how many of those outcomes do we have as opposed to the total number of possible outcomes? So in the case of the lotto ticket, okay, if you want to win the jackpot, your chances are about 1 over 300 million. Okay, that's your chances of winning the jackpot. Okay. On the other hand, if you want to figure out the chances of winning a lesser prize, let's work that out, okay? Because I do want to kind of provide the context of what I said here. So let's just say that you want to, out of the five winning numbers, you want to have three of the, oops, okay, there we go, three of the winning numbers, and you also want to match the Powerball number. So this is the exact price that you want to calculate and go like, what are the chances that my lotto ticket will get this particular price? Okay. So how do we figure that out? Yep. Right. So let's work out the easy part first. Okay. The easy part is in this case, what is the cardinality of big omega? Big omega normally, without using the number and the stuff in parentheses, is representing the set of outcomes. In this case, we are looking at all the possible tickets. So the possible tickets, okay, we actually talked about this a little bit before. So in this case, it is five because there are five numbers per ticket, and also there are five winning numbers. Out of the five winning numbers, I need three of those. So that means I need two more numbers on my ticket that is chosen from the non-winning numbers. There are 69 numbers to begin with. So if five are winning numbers, how many non-winning numbers do we have? 64. Very good. Okay. So this particular number, which is 5 choose 3 times 64 choose 2, is representing the number of tickets, not considering the Powerball number. So if we throw the Powerball number out, then this would be the total number of ways that you can buy a lotto ticket or unique lotto tickets. But since the Powerball number is actually important to us, now we have to say, okay, we have to remember to multiply the number of ways to choose one Powerball out of the total number of Powerballs. How many Powerball numbers do we have? 26. So we now say, okay, we have 26, choose one of them. So this is approximately what we calculated to be 300 million. Is that okay? So the next thing we need to do is to say, okay, but there's a specific price that I'm interested in, and we want to figure out, how many of those tickets do we have. So this is going to define what is the event set. So in this case, the event set is going to be a set of lotto tickets that are like this. Okay, I want this set to be all the lotto tickets that has three of the winning numbers and um Okay, I take it back. I did something that's horrible because the total number of tickets is not this number here. You know, I messed up because in my mind I was merging the two numbers together. So let me fix this. So the actual total number of tickets is uh, 69 choose 5 times 26 choose 1. That's it. Because the actual winning number is 60. There are 69 numbers to begin with. There are five numbers on each ticket. So that takes care of the five numbers other than the Powerball number. There are 26 possible Powerball number of which we choose one. So that is the correct equation. So I do apologize that I was merging the event set with the actual outcome set. Yep. No, this is a number. This is really just cardinality, which is a natural number. So now we have to look at the cardinality of E. So this is where we use the other equation. Because once we have a drawing, we already know the five winning numbers. Of the five winning numbers, I need three. Of the non-winning numbers, there's 64 of those, I need two. And we need to multiply because for every way to choose three out of the five winning numbers, there are this many ways, 64 choose too many ways to choose the non-winning numbers on the ticket. So that's why they're multiplied. And then this also times one because out of the winning, the actual Powerball number, I want that. So that means there's only one way to do that. Is that okay? So now we can do the probability. So the probability is really the cardinality of E divided by the cardinality of omega. That ratio is the probability. So this is why it is important to understand how to do the counting because we need to know how to do the counting for the event set. We need to know how to do the counting for omega. So once we have those two numbers, then you know the probability. So are we doing okay so far? Okay. Yep. How do I get what? You mean this one? Because I want to look at five winning numbers in my ticket plus matching the Powerball. So out of the five winning numbers out of a drawing, I need only three of those because that's the price that I'm interested in. But then I have only specified three of the five numbers. What about the other two? Well, the other two numbers have to be coming from the non-winning numbers, and there are 64 to choose from because there are 69 numbers to begin with. Five of those are already designated as winning numbers, so there are 64 non-winning numbers, of which we need to choose two. The Powerball number is already chosen, and I want it. So that's why this is one choose one. Okay, very good. All right. So I think a lot of these questions, especially in the final exam, are word questions. Okay, because basically you have to understand what the problem is, what we are interested in, and also what is the total number of possible ways to do a certain thing. So we can talk about some of the practice questions when we have time when we get to that point. Is that okay so far? Yep. Yes. So basically we already have drawn the five winning numbers and the Powerball number. We are only trying to calculate what are my chances of getting that particular price, a specific price. So in this case, because the original problem said that I do want to match the Powerball number because I get more money when you match the Powerball number. But there's only one chosen Powerball number. That's where this one is coming from, and I want that, and that's why we get this one here. So we can work on a similar problem. Okay, so let's just say that you want to try something where you have four of the five winning numbers and no and not a match for the Powerball. Okay, so we will try to figure out the probability of this one. So the probability of this one is going to be out of the five winning numbers, this time you want four of those. So that means out of the 64 non-winning numbers, you just need one of those. And on top of that, out of the 25 non-Powerball numbers, you need one of those because there are 26 numbers to choose from for the Powerball number. And this time I specifically said, okay, let's not match the Powerball number. So there are only 25 of non-winning or non-chosen Powerball numbers, of which I need to choose one of those. So when you divide this whole thing by the total number of possible tickets, that is, 69 choose 5 times 26 choose 1, which is the same number as up here. Then you have the probability of winning of your ticket, winning the specific prize of matching four of the five winning numbers, but you're not matching the Powerball number. Is that okay? All right. So let's go ahead and see if we can apply what we have just learned today to a somewhat interesting problem. Okay, because I want to know, okay, depending on the jackpot, how many people are playing or how many, you know, tickets are sold. Okay. The number of tickets sold is not necessarily the number of people who are playing because one person can buy multiple tickets. Okay. So now what we do is we are going back to here and then we go to the Lotto website, California Lotto Lottery. And then we go to Powerball. There we go. And it shows the latest drawing. So what is the latest jackpot? It doesn't show? Right here. Okay, $20 million. Obviously not worth playing because your chances of winning the jackpot is 1 in 300 million. Okay, this is not even close, not even in the right ballpark. Okay, but what we want to know is how many people bought tickets. Okay, total. So we can probably tell, how many people bought tickets as a total. So what we do is we go to past winning numbers, and then we look for a specific price. Okay, let's say the price that we are looking at, which is only having four of the five winning numbers, but not the Powerball matching. That actually will net you $408. So not too shabby. Okay, there are only 44 people who won that prize in the previous drawing. Okay, so now the question is, from this, can we tell the total number of lotto tickets sold? Okay, it's a ratio metric kind of thing. Okay, so if your answer is yes, because you intuitively understand, oh, okay, it's just a ratio. If we know the probability of this and we know exactly 44 people got this ticket, we can estimate, okay, as a ratio from the ratio of how many people actually bought a lotto, how many lotto tickets were sold. We can have a little estimate of that. Okay, so for this, we're going to actually do some calculation. So I'm going to go to the Google Drive and go to the folder for this class because this way, all the math being done will be captured by a spreadsheet that you have access to. So this way, if you want to review any of the math that we talked about today, in addition to rewatching the video, reviewing your own notes, you can actually go to the spreadsheet because that gives you a eh, kind of different way of representing what we talked about today. So we go to Google Sheets and create it in this folder. So that means as soon as I change the file name, you can have access to it from your own computer or mobile device, whatever you want to use. Today is 0428, I think. Yep. All right. So now I will try to comment everything here. So we'll say the number of tickets with four winning numbers, no Powerball. Okay, so that's going to be the calculation that I showed you a little bit earlier. Okay, so I'm going to type it in the Excel format, which is combine for combination. So out of 5 out of 4, no, 4 out of 5 winning numbers, um, of the 64 non-winning numbers, we need one. And also of the 25 non-matching Powerball numbers, we also need one. So this is the total number of tickets that the total number of unique tickets that can win this particular prize, 8,000 of those. And then what we do is, right, so the total number of unique lotto tickets, okay, so we need that too. And that would be the combination of 69 choose 5, because that's how the numbers are drawn, times. Now, this one, I want to put it this way, okay, even though we all know it's just 26, but I do want to emphasize that it is 26 choose 1, which turns out to be just 26, okay? So that is, what did I, oh, I forgot to, oh, syntax error, I mistyped. There we go, the 300 million thing. So now we look at number of tickets that won the specific prize. That turns out to be what, 44? Okay. So now I want to know, estimated number of tickets sold. So that's going to be a ratio metric kind of thing. Can somebody tell me, how do we get to this number? So 8,000 to 300 million should be the same as 44 to whatever this cell has. Okay. Um, Let me write it in the tablet so that you guys can visualize the equation and then attempt to solve it. So we know that 8,000 divided by 300 million should be approximately the same thing as 44 divided by the unknown that we are trying to solve here. So I hope you guys all feel comfortable solving for x here. Yeah, I mean, however you want to call that. I don't know the terms of these things, so move x over here. So now on this side we have 44 times 300 million divided by 8,000, I think. That doesn't seem right, does it? Yeah, that looks right to me. Yeah, that looks right to me. Yep, okay. So we'll go ahead and turn this into an actual equation. Okay, so we are multiplying this number by this number and then divided by this number over here. And so we have approximately what, 1.6 million tickets sold? That's an estimate. So that can be helpful because if you keep track of all of these things, and the website actually has historical records of how many people won which prize and so on and so forth. So you can now come up with a model using a neural net, right? You can come up with a model of how the jackpot maps to total numbers of the total number of tickets sold. Yep. So that means, approximately, according to this one single data point, we think there are approximately 1.6 million tickets sold for that week. It is never really exact, because so you can do the same thing to all of the other data points, which means you look at the total number of 3 plus Powerball, one, and then you multiply, do the same math with this one to try to figure out the total number of tickets sold. They will all be slightly different because it's not exact. We're trying to make use of uh, available data to backfill things that we do not know. You can do that too. Okay, so if you add them all and then you ask how many people will win at least once, win something out of the whole thing, and then you divide and then you do the same math, then you can probably get a better estimate using that method because it's basically the same thing as averaging. All right. So are you guys seeing the potential application of probability? Okay, cool. All right. So now with that said, we are moving on. And I really hope that you guys have been keeping up with reading the notes because not doing that is not going to help for sure. So now we are moving on to this slide here. It's called discrete probability, which also has a whole bunch of math stuff in it, as you probably suspected. Let's see. This is still using my Power website. Okay, I'm gonna. Hmm, I haven't switched over to the GitHub yet, but that's okay. The content is the same. All right. So over here, it just section two just talked about something that I just talked about, which is event. The event set would be things that you're interested in. Okay, like what are the how, it will be the tickets that win a particular prize or not winning at all. Okay, it'll be things that you're interested in. And then omega is the total number, is the set of all possible outcomes. So the ratio between their cardinalities will give you the probability, which is exactly what we just did. We talked about the birthday problem already, so we're gonna skip over this section here. So now we're moving on to tossing coins. Okay, now this one is kind of interesting because it will lead us to a different kind of probability distribution. So the example says if I were to toss a coin, assuming it is not loaded, okay, so for the time being, we assume the coin has 50-50 chance landing on the head versus a tail. And the outcome of tossing that coin exactly 5 times is what are the chances that we end up with 3 heads and 2 tails? Okay, so how do we figure that out? So we go like, oh, okay, it's a probability thing. We try to look at the event set, we look at the omega set, we then look at the ratio between their cardinalities, and then we have the probability. Okay, that's exactly what we're going to do. So now the question is, we'll work with omega first. Okay, so what do you think are the okay? First of all, how many um, possible outcomes do we have if we are to consider ordering to be important? How many ways can we get 3 heads and 2 tails? Okay, what if it is not important? What if ordering is not important? How many ways can we figure out? How many ways can we end up with 3 heads and 2 tails? So looking at the projector is not going to help you. So what are you going to do? If my question is if ordering is important, okay, so ordering is important, so that means head, 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 tail, tail is considered to be different from tail, tail, head, 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 okay? So given that is important, how do you know how many ways we can end up with 3 heads and 2 tails? Yes, it's it is not permutation, okay? You use permutation when you conduct trials without replacement, which in this case means if I toss a coin, it lands on the head, the coin cannot land on the head anymore. I don't think coins work that way, right? So this is with replacement. Okay, so I know how much you guys like visual representation, so I'll give you visual representation. Okay, this is the starting point of the experiment. We end up with 2 possible outcomes, right? The first toss ends up with either head or tail. Okay. What about the second toss? It can be head, can be tail. What about the third toss? What do you think? I think you guys are getting the picture. Fourth toss, same thing. I have to write smaller now. Yep, I'm running out of room. Did not plan well, but that's okay. I'm not an arborist, so I'm not going to frown at this tree. An arborist would look at this tree and go like, "Who did the trimming on this tree? That person should be fired." But since I'm not an arborist, they cannot fire me. Okay, that's only four tosses. We said five, right? Okay, so okay, I think you guys get the general idea. Okay, and finally, whew, just enough space. Whew, cool. How many leaf nodes do we have? 32, because it is 2 to the power of 5. Because the branching factor stays the same for every level of this tree. So that's why we have 2 to the power of 5, because the branch factor is 2. So for each level of the tree, we basically double the number of nodes. So by the time we get to the leaf nodes, there are 32 of those. Okay, so let's pick one random leaf node and say, okay, what is that representing, Tech? Okay, so we'll pick this one here. Okay, we'll try to figure out, what this one is representing. So to get to here, I first have to get a tail, right? And then we get a head. Okay, and then we get another head, and then we get a tail. And then we get a head because the top one is the head, the bottom one is the tail. Ah, okay. Coincidentally, this one does meet the requirement. This is what I'm looking for because it has three heads and two tails out of five. Now, that is just totally luck on my part, and you can calculate the chances of that. We'll get to that. Okay. All right. So I'm beginning the idea of how we can figure out all the possible ways to end up with um, heads and tails from five coin tosses. So now we want to figure out how many of these leaf nodes meet the requirement of three heads and two tails. I don't, so this time I don't even care where they are. I just need to know how many of these end up with three heads and two tails. So how do you figure out that number? Now you can, well, okay, we'll talk about the most obvious way first. The most obvious way is you do this, but on a much larger piece of paper, and you just work out the actual 32 possible cases. Or you write a program to do it. The quickest program I can write to do this would be like this. We got time. I can show you the program to do this. All right, come on. There we go. All right, all right. So we'll say coin.c. Okay. Pound include stdio.h and main, and then we'll use macro definition because I can do stuff that you know without macro it would be hard to do. Okay, so it's for x equals to 0, x is less than 2, x plus plus. So that will set up, oh, I need to also define the header, which is coin x. There we go. All right. So now we have five variables, one for each toss, right? So we'll have int t1, t2, t3, t4, t5. Using an array would make more sense, but I'm going to go for the really quick and dirty approach. Okay. So we say coin t1, copy and paste, 2, 3, 4, 5. Oops, 5 right here. And then I'm going to use another macro to do some funky stuff here. So define, I would call that head tail, okay? And we'll take an integer here. So we'll go like if I is true, then we print a head. Otherwise, we print a tail. Okay, and put it in parentheses just in case I need to do that. Print f percent %c, percent %c, percent %c, percent %c, percent %c, percent %c, line feed, and it will be xt of t1. Okay, put a comma here, and then use the lazy approach of copy and paste. T2, uh, copy to the end, paste, paste, get rid of that. This would be T5, T4, T3, T2, T1. Okay, I think that's it. Return 0. Okay. All right. Does everybody understand this program? Because you guys all told me that you have met the prerequisite of CISP 360. I'm just checking here. I bet you they didn't tell you anything about macros. Macros, which is signified by pound define, is a syntactic operation, purely syntactic operation, with no semantic checking whatsoever. It's done by what we call the C preprocessor. Okay, so the C preprocessor will basically look at coin in this case, expand it based on the macro definition into four, and then T1 equals 0, T1 is less than 2, T1 plus plus, and so on. And then after the C preprocessor is done expanding the macros, then it will pass it on to the actual C compiler, which will then actually look at the structure of the program and put the whole thing together. Okay, but it is a really handy feature to use when you want things to be quick and dirty. Yes. Macros do not need a semicolon. Depending, it depends on how the macro is supposed to be used. In this case, it doesn't need a semicolon because I really need the loops to be stacking or nested, so I don't want to include the semicolon. All right, so we just go like, show me the coins, show me the coins. There you go. All right. So to do this in a recursive way is a little bit harder, but not super duper hard. Okay. But to come up with something like this kind of quick and dirty approach, I really think people of this class, students of this class should be able to do this. Okay. Now, how long did I use to do it? 5 minutes. Okay. Now, I promise you, I did not memorize the code. Okay. Even if I wanted to, I cannot remember stuff. Okay. Um, but you can say that I have taught this class many, many times, so you can kind of use that as an argument and go like, but Tech, we cannot compare you to the students in this class. So WC, it stands for word count, not water closet. And there are 32 lines and 32 words from the output of that program. So I just did a quick sanity check to see whether the outcomes are is correct or not. But given this is what we want, now we can go like, how do we find out how many of these have three H and um, basically two T's? Well, but grab word count does not tell you which one qualifies and which one does not qualify. So you need a grep of some kind to look for that pattern. So you need grep. We need exactly three T's. So that means four T's would not qualify. We need exactly three T's. That can be a little difficult. Okay. So instead of spending time here to talk about how to do that, let's just do some actual manual counting. All right. So we just go through the list here. Here's one. Nope. Oh, we're counting three heads, right? So this is one, two, three. Oh, I just lost track. Okay. Because I do a space bar and scroll down. Okay. Let's do it one more time. Okay. One, two, three. This is four, five, six, 7, 8, 9. So there are 9 of those. Okay, I could have miscounted. But the question is, can we do this without this stupid kind of counting? Can we use an equation to do this? As it turns out, yes, we can. And we can actually reuse something that we have learned already, which is the number of, okay, I'll give you guys a choice here, the number of permutations or the number of combinations, because you thought it is order dependent. But the answer is actually the number of combinations. So the way we do this is you can imagine, okay, because I think you guys like visualization. So imagine you have a bag, okay, and in the bag we have all the possible positions of the coins, okay, the first toss, second toss, third, fourth, and fifth. So that means we have 1, 2, 3, 4, 5 in it, okay, and I need to pick 3 items out of the bag to represent where the heads are. So that means I'm choosing 3 out of 5. Okay. So that means I want to pick 3 of these, put it into a smaller bag, and say, okay, which 3 number did I choose so that I know where the heads are in a 5 toss experiment. Okay. So that means what we are really looking at is 5 choose 3. So 5 choose 3 is what? 5 factorial is 120 because it's 5 times 4 times 3 times 2 times 1. I think that's 120 divided by 3 factorial times 2 factorial. So that is 6. This is 2. So that means I should have 10. I miscounted 1. Don't know where that one is supposed to be, but we can also systematically print all 10 possible ways to have 3 heads out of 5 tosses. So we can have tail, tail, head, 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 tail, head, tail, head, 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 tail, tail, head, head, and then we have head, tail, head, tail, head. I'm not being very systematic here. Head, tail, head, head, tail, and then we can, except for this one, everything has a flip one, so we can now have head, 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 tail, tail. This one is head, head, tail, head, tail, head, head, tail, tail, head. This one, the reverse is exactly the same. Now we have tail, head, head, tail, head. I'm missing one. Okay, which one am I missing? Oh, nope, that's not it. Head, tail, tail, head, 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 tail, tail, head, 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 tail, head. I think I'm missing head, head, tail, tail, head. Am I double counting this one? Yep, it's the same. Which one now? Huh? Tail, head, 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 tail. Yep. Okay. So that's the other symmetric one that I missed. Yep. So there are 10 of these. Okay. So please read the notes. Okay. And we'll continue with this on Wednesday. Yep. I cannot hear you. Sorry. Um, the number of tosses, number of heads. Yes, because if you think about the 5 possible positions, I'm trying to say, okay, of those 5 possible positions, which ones do I want to be heads? So that's how you kind of reformat a question into something that we already know. Okay, do you remember this notation? How do you evaluate it? But that's why I asked you whether you remember the notation. Well, Then you have to go find it. Yep. Yes. Yep. Well, we do. So we want exactly three heads, which means the other two must be tails. So we are not looking for at least three heads. We are looking at exactly three heads. So we are looking at how many ways can you end up with three heads given that you have five coin tosses. All right. I think you figure out what?